Hello, people. The next element of our look into forces and Newton's laws talks about objects on inclines or ramps. So here's an object on a ramp. There it is. This ramp, we will say, is inclined at an angle measured from the horizontal that we'll call theta. And this object has a mass little m, and here's the gravitational force mg acting on this object. Now, there's not much of a situation described here, and so for that reason, the only thing that we know for sure is, just like any object, there's always a gravitational force acting on it. And in this case, there is a normal force acting on this object because of the surface contact between ramp and block. And that normal force is going to look something like that. On block by ramp, if you like. Yeah, sure. Sure. On block by ramp. Okay, now, thus far, what we would do is probably break forces into components and write net F equations in horizontal and vertical directions. And we're not going to do that here because if this object is going to accelerate, which in this case it will, right? We don't know if this, we haven't talked about friction, we don't know if anything's pushing or pulling on this thing. For sure, these two forces are acting on this object, all right? And also for sure, if this object is going to accelerate, it's going to be in one of these two directions. Now, what I wish I had done, don't draw that yet, what I wish I had done is made that a dotted line. I don't want to say those are forces because they're not, but what I am saying is if this object is going to accelerate, it's going to be either this way or this way. And so guess what? For that reason, that's a direction that we ought to investigate. We ought to look at forces that point in that direction. And if we're going to look at forces that point in that direction, what we also have to do is look at forces that point perpendicular to that. All right, so the reason that so far we've done a lot of this, let's do net force in the x, net force in the y, well, is not just because horizontal and vertical are, friendly directions to talk about. I mean, they are because in a lot of cases, things accelerate across tabletops. What about an object that's in free fall? It only moves vertically. And so the reason that we used x and y coordinates like this so far is a couple reasons. One is they're perpendicular, right? And we can talk about forces like this. I wouldn't draw all this stuff if I were you. We can talk about forces like this, and then we can talk about forces like this in two different expressions because our blue horizontal forces have nothing at all to do with vertical acceleration. Our red vertical forces have nothing at all to do with horizontal acceleration. And the reason that is because they are perpendicular. So as long as we use any axes that are perpendicular, it actually doesn't matter which ones you use. We use x and y, again, typically horizontal and vertical, because things, sure, accelerate across tabletops, or accelerate vertically due to free fall, something or other. Okay, but in this case, in our case of an object on an incline, the direction that this object will accelerate is most likely going to be up the incline if it's pushed or pulled hard enough, or down the incline if it's, perhaps sliding down on a smooth surface. All right, so we're going to use these new axes as our axes. Other nice thing is that, if you imagine a frictional force, it's going to be parallel to this surface, so that'll point in one of our coordinate directions. Normal forces by definition are perpendicular to surfaces, and one of our axes is perpendicular to the surface, so normal force is along an axis. mg is off axis. mg has components that point both perpendicular and parallel to the incline. And I actually call these axes, I don't call them x and y anymore, I call them parallel and perpendicular. Parallel to the direction this system or object will most likely accelerate. Perpendicular to the direction this system will accelerate, if it accelerates. Okay? And so, here's what we have to do. We have to be able to construct the components of mg that point in our new coordinate directions. And so what we do is we take, well, again, don't draw this, but if we had a force acting like this on an object on a on a horizontal surface, what we do, whether or not you are paying too much attention to this, is what I do at least. The way I think about it is I say, this is how far to the right this thing goes, this is how far up that thing goes. I draw these little, you can draw these little dotted lines from the end of the actual force along to the coordinate axes that we use, right? So I've made, perpendiculars from, here's our axes, and I make these perpendiculars from the end of the vector to those axes, and I'll do the same thing here, all right? And I want you to notice that when I draw this, I'm not drawing it horizontal, right? And when I do this, I'm not drawing it vertical. I'm saying how far along our coordinate axes does this vector, this mg vector point? And part of it that I'll call mg parallel is that long. And another part of it that I'll call mg perpendicular is that long. Don't draw this, but here's what people will do incorrectly. Don't draw this. People will say, people get pretty good with, here's object, here's incline, here's mg. People do okay. What they'll do is they'll say, all right, the components look like that. Well, that's wrong because the components are supposed to be perpendicular. That's one thing. The other thing is this does not point parallel or perpendicular to the direction this thing is going to likely accelerate. So this vector ain't no good. It's not a part of, notice this is bigger than the whole mg force. So that can't be a component of it. Components can't be bigger than the whole force. So we have to make sure, like we've done correctly in our actual diagram to the left, that our components of mg are perpendicular to each other and point along the directions of our new coordinate axes. Okay? Now let me clean this up a little bit. That's not good. That's better. Now, what happens to work out is this angle theta here is part of a triangle, and let's see, that triangle, at the risk of muddying up this composition, what I'm going to tell you is, well, watch this. Don't draw. I'll get rid of this stuff in a minute. Here is a right triangle, right? And here's another right triangle. Yeah? And those are similar triangles. And so this angle theta here is also this angle in the blue triangle there. All right? If you look closely, check this out. This angle, if this is theta, then this one in the red triangle is 90 minus theta, because here's 90. So like if this were 90 and this were 30, this would be 60. Right, 90 minus 30 is 60, 90 minus theta. And here's another, I know it's starting to get ugly, here's another right angle here. And so if the green is 90 minus theta, well then the blue, again, this blue theta, again, has to be 90 minus that, or 90 minus theta. So it's theta. Okay? So, as long as you can feel okay with, you can either accept my geometric proof, or you can take my word for it. The angle that this ramp is inclined at is always that angle inside that, between mg and mg perpendicular. Okay, and for that reason, notice mg parallel, if we want, we can draw it down here. It's nice to draw it up here because then it looks like it actually acts on the object. But if mg parallel is down here, we notice that mg parallel is opposite that angle, and mg is the hypotenuse of that right triangle. So the things you must be able to recognize for an object on an incline is that there is a component of mg parallel to the incline that we find using mg sine theta. All right, as a little proof, and I wouldn't, if you don't want to write this, don't write it, but notice sine theta is opposite mg parallel over hypotenuse mg, thus yes. Okay? And similarly, or not coincidentally, mg perpendicular is adjacent to that angle, where mg again is the hypotenuse. So this goes as mg cosine theta. If you need a trigonometric proof of that, I recommend you start with the definition of cosine and see that what I've written is true. Okay? So, this is the key to handling any question about an object on an incline. All right? We have to rotate our axes. Now notice, hang on. Yeah, well, just notice, if what we're really sort of doing, you can think of it in a couple of ways, but we can think of it as sort of, oh boy, that's okay. We can sort of pretend that what we're doing is taking this thing and saying, yeah, it's sort of like this. It's sort of like the old object on a table where we need to look at components of vectors that are are along the surface and perpendicular to that, right? And so, since mg now looks off axis, it looks like it's down to the left. Mg parallel is the component that points left. Mg perpendicular is the component that points down. Okay? But we're just, instead of rotating our sheet of paper, we're just rotating our axes. Okay? Okay, so here's a couple of applications. Object slides down a frictionless ramp, inclined at angle theta, find its acceleration. Okay, so start as a good free body diagram. I really like to draw free body diagrams big when I do incline stuff. It helps me justify that if there's theta, there's n, frictionless, slides, that's it. Those are all the forces. All right, I'm now going to sketch my mg parallel, my mg perp. Notice mg parallel does not point left, it points down the hill. Mg perpendicular only goes as far along this perpendicular axis as mg goes. All right? Find its acceleration. Well, the only force that makes this thing accelerate is a component of mg. And so if we do a net F in the parallel direction, we get mg parallel equals ma. That's it. Mg parallel, we said, is mg sine theta. This angle here is the same as that angle there. Mg parallel can be drawn there if we want. And thus it doesn't matter what the mass of this object is. It accelerates at a rate g sine theta. Which makes sense because what if at theta equals 0, right, which means this angle goes to nothing, which means the incline is not inclined, then a is g times the sine of 0, which is 0. A is 0. At theta is 90 degrees, it means this is cranked all the way up to being vertical, and then this thing is simply in free fall. A is g times the sine of 90. Sine of 90 is 1. A is g. Yeah, the thing's in free fall. Okay? Okay. Okay, pulled up a frictionless ramp, inclined at angle theta. Slides at, constant speed, constant speed. What tension is required? Okay, okay. Oddly enough, free body diagram. Oy. Mg. We've got a normal force. Now I can do this pretty darn what's the word I'm looking for, accurately, because let's see, this is about the size of mg parallel. This is about the size of mg perpendicular, and I happen to, look, I picked normal force pretty accurately because you notice that since this object does not accelerate in the direction perpendicular to the incline, those two forces must be equal and opposite. Okay, and if we're going to have this thing slide up the ramp at a constant speed, that means A parallel is 0, and it means that this force, T, and mg have to be the same size. This object has to be in equilibrium. The net force acting on it has to be 0. So if I write my net F, I'll do it in the parallel direction, I get T minus mg parallel equals ma parallel, but A parallel is 0, Gonski, and I get T equals mg parallel. T equals mg sine theta. Fair enough? Okay. Ooh, look at this sliding down to the right. Crazy. Slides down, there's a frictional force. What's the acceleration? Okay, okay. Okay, so free body diagram. There's mg. There's a normal force like yay. There's a friction force that we don't know how big it is. I'll draw it like that. Notice it's sliding down the ramp, hence friction force points up the ramp. All right, here's a mg parallel. Here's mg perp. Here's angle of inclination theta. There's theta. Find the crate's acceleration. Okay, so let's see. I'm writing net F parallel, because if it's going to accelerate, it's going to be parallel to the incline. So arbitrarily, I'm going to say mg parallel minus the friction force is ma parallel. I have defined this way to be the positive direction because I can. All right. So all we can say is A parallel is mg sine theta minus the friction force divided by m. Okay, and this tells us a couple of things. It tells us, well, our A will be positive if this term is bigger than this term. And positive means down the slope. This thing will speed up. It's sliding down the ramp, so if mg parallel is bigger than the friction force, it speeds up on the way down. If the friction force is bigger than mg sine theta, then the top of this fraction is negative. The acceleration is negative, which means the net force and the acceleration are that way. And if it's sliding down the ramp but accelerating up the ramp, it would slow down until it stops. Okay? But since we don't know much detail about the question, all we can say is that's the best answer. What force does the ramp exert on the mass? Well, that is this force. That is on mass by ramp. All right, that is a force that points in the direction perpendicular to the incline. So if we do a net F perp, we can say N minus mg perpendicular is 0. We get N equals mg perpendicular. We get N equals mg cosine theta. People get, at some introductory points in looking at dynamics, people get very used to saying N equals mg. I've seen it like that lots of times, but there are many cases when that's not the case. Here's one of them. Okay? All right. We'll leave this one till I see you in class, unless I don't have you in class and you want to solve on your own. I will tell you that the tension on the rope is 50 newtons, assuming G is 10 newtons per kilogram. And the answer here, there is friction. Notice the system is not moving. That friction force is about 56 newtons up the hill, if you're solving at home. Okay? All right. The bread and butter of any incline question is to be able to handle the fact that the components of mg, perpendicular and parallel to the incline itself, can be expressed like you see in the green box. Okay? As long as you can do that, you can solve an incline problem fairly well.